Hi, this video finishes our treatment of the queue data structure. We're going to analyze the two alternative implementations we saw and see what their trade-offs are. So remember, we've implemented the queue abstract data type, and the major operations of the queue are nqx, which adds x to the back of the queue, front, which returns the element at the front of the queue, and dq, which removes the element at the front of the queue. Together, these create a first in, first out queue, which corresponds to a fair line. The first implementation we looked at was the linked list based queue. It uses a singly linked list to implement nq, front, and dq. And then we looked at the vector based queue, which uses a partially filled vector to implement the same operations. The vector based queue ended up being more complicated. There was this wraparound issue where once our indices got to be so high that they might go out of bounds, we had to recycle index 0, and we call that wraparound. We use modulo arithmetic to implement that. And then we also needed the resizing feature, which is that if the vector-based queue gets completely full, then we resize, meaning allocate a larger vector object and copy everything over. So let's look at the asymptotic efficiency of these two alternatives. What we've got here is the list of the major queue operations. In the middle column, we have the asymptotic efficiency of the linked list version, and in the right column, we have the vector version. The constructor, which creates an empty queue, takes constant time for both data structures. The size accessor that gets the size of the queue is constant for both data structures. nq is constant worst case time for the linked list based queue because it's just adding a node to the linked list. For the vector based queue, it's constant amortized time because of the possibility of resizing. So they're both constant time and very fast. But the vector-based queue, we have to say amortized to be transparent about the fact that sometimes there's a slow resize event. Front is constant worst case time for both data structures, and dq is just like nq. dq is constant worst case time for the linked list and constant amortized time for the vector-based queue due to possible resizing. So let's see how these two compare to each other. We've got the same trade-off that we had for the stack alternatives last week. So both the linked list based queue and the vector based queue are efficient. All of these operations are constant time. Big O of 1 is the fastest possible asymptotic efficiency. So they're both fast. They're both good. The vector based mutation operations are constant amortized time. Mutation means changing something. So in this chart, the only negative I can see for vector-based queue is that when you add or remove an element, it's constant amortized time, and we have to say that because there's the possibility of resizing. And that can be a negative in some applications. If you really need predictable performance and you can't deal with an occasional glitch where the queue is a little bit slower sometimes, that amortized time due to the resizing could be a negative for the vector. However, the vector-based queue has better constant factors. You might remember that the constant factor is just the measure of how much time and memory it takes for the computer to implement these operations. And comparing big O of 1 to big O of 1, the vector is faster because of the nature of how CPU caches work and how pointers work. So because of that, our decision is for a general purpose queue, use the vector-based queue. Both data structures have constant time operations. They're both super fast. So the tiebreaker is the constant factors, and in general, the vector-based queue is the better one to use. But if that amortized aspect of the nq and dq operations is unacceptable to you and you need consistent time per operation, that's where the linked list-based queue would win out. So to summarize that, here's the same table again, and the list-based queue is constant worst case time for all of these operations. The vector-based queue is constant time for all these operations. The one catch is that the nq and dq are constant amortized time.